Okay, all right. So these questions that you see here, they go through the scope of different things that we covered, which we started off with the limits, then we went into the derivatives, and these are the two big topics we sort of seen. Alrighty, so the first question is giving you a function that define piecewisely, but more importantly, that you're given a picture of it. And the picture has, how many pieces do we see? 1, 2, 3, 4, 5. So there are 5 different pieces. And the question, let's see what the question is asking us to do. Determine all points where the graph is not continuous on the open interval -1 to 5, and also say whether discontinuity is removable or not. So if we go here and we start looking at this, right? The graph starts at -1. It says, to start looking at this point right here. And we go up to 5. Over the course of this graph, if you go from left to right, you can also see the definition of the function that is right here, right? The piecewise stuff. Starting at -1, the first break that you see is where. And when we say where, in calculus, where? First, you got to look at the x coordinate. X, not the y, x. So what is the first x you see where you have a trouble? You go from left to right. Starting at -1, where's the first problem that you see? And I printed out for you so it's easier for you to see, right? X equals to 0 is the first troublemaker. So let's go ahead and kind of highlight it over here. So the first troublemaker is right here. And you see there's a gap going on, right? In between. And again, it's printed, so it's easier for you to see in the printed version than on the screen here. But if you see there's a gap, and because of that gap, we have that the function is not, well, you're right, you're saying non-removable. Excellent, right? So not only it is discontinuous, but it's also non-removable. So let's write it down. So x equals to 0 is our first discontinuity. And you say that this is non-removable or removable. Why? You see a jump. Okay, fine. So a jump. Can we be more calculus language-wise? Limit from the left doesn't equal to limit from the right. Limit does not exist. Let's be even more specific. If you go from the left, since we're reviewing right now, right? Since you're going from the left, look at the picture and also connect it to the equation. Looking at the graph, as you're approaching from the left, where does the graph go? From the left. It goes to 1. Do you see it? All right, so it equals to 1. Do you see it in the equation? The way it's defined right here. Yeah. How would you know?
If you plug in 0, it'll be 1. Because 0 squared is 0 plus 1 equals 1.
Absolutely. Once you substitute 0 in the left side, you're going to get 1. You want to make those connections, geometry, and the definition of the piecewise function. How about on the other side? Limit as x approaches 0 from the right side of f of x. It's 0. Yes. Let me erase this right here so you can see it better. It's a very important point, right? We're talking about limits and we're connecting to the concept of continuity. On the left side, it's 1. On the right side is, you see it visually, there's a gap. There's a gap, visual, right? You can also see if you substitute 0 inside here, you also get a 0. You also see it in the definition. So you see the gap, because the limit from the left doesn't equal to the limit on the right, that limit itself does not exist. So limit does not exist, limit. And remember, when we talk about the limits, when the limit is D and E, when it's not a number, the discontinuity that is there is removable or non-removable. Not, that's what justifies discontinuity. It's non-removable. By the way, is there f of 0? It's not clearly seen from the graph. All right. But of course, if I give this, now this was my earlier question. This was from like an earlier on when I started teaching calculus. I had that example. So yeah, it was not really seen, really well here. But you do see a little holes. If you zoom in the graph, I mean, it's hard to see even there. But how would you know it from the function? There's no equal sign next to the 0. Notice there's no equality here and there's no equality there. So f of 0 then is just does not exist. Bless you now, the fact that the point is not there, that's right away tells us that it's discontinuous. But the fact that the limit does not exist tells us more information. So the discontinuity is not removable. Okay, let's go a little bit quicker with the other one. So how about how about the next point? So at 0, we discussed there's a jump, non-removable discontinuity. Let's continue going. We're going. Any trouble here? Well, yes, 3 will get to there. Before 3, there's an in trouble between 1 and 3. I mean, between 0 and 3. X equals to 1. If you look at the 1, notice there's here not clear. It looks like there's a hole, and it's maybe printed a little bit better there. But you also see that there's a point on the bottom clearly defined to be something else. You see that the point is not someplace else. Also notice right here is that f of 1 does exist. What is f of 1? It exists. So point is there, but you see that the point is misplaced. So x equals to 1 is a troublemaker. So what's the problem? What's the limit as x approaches 1? It's 5. It's right here. Notice that the limit on the left is 5. From the left side and from the right side, it wants to be at 5. You can also see that from the equation. If you plug it in 1, inside here, you get 5. If you plug it in 1 inside here, you also get 5. So it matches the 2 branches are meeting. However, the point is displaced somewhere else. Okay, so what do we say? It is, the point is at -4, the limit is 5, so they're not matching. Therefore, what do we say? Is it continuous? No, we already said that x equals to 1 is a problem. So it's not continuous. Why?
The point that is defined in the limit.
Well, limit does exist.
I mean, they don't match each other.
They don't match each other. They don't match each other. They're different values. So they're not equal. That's why it's not continuous, that the limit and the point do not match. Now, the next follow-up question is, of course, to say whether it's removable or non-removable. Why? Oh, this is cool. Okay, I gotta stop. All right. Yeah, it's removable because limit on both sides is the same. Is that the limit is it wants to be at 5. Some reason, the author of the question decided to place, well, not for some reason. I want to show you an example of where you have both branches meeting on 5. Not like here, when one side it was 0, on the other side is 1. Here on both sides it's 5. You see it visually that it's 5, but the point is displaced somewhere else. Okay, but the limit exists. Therefore, that one point can be simply redefined. And if you move that point and you put it inside here, that's when it will make it removable. Okay, so limit is the key to continuity. All right. So on, when you're preparing your little note sheet, whatever, for the exam, Remember just to write for yourself is that the limit is what determines whether something is continuous or not. And it gives you also information about whether discontinuity is removable or not. Yes. You say it's removable because the limit exists. That's how you say it. You say it's removable because the limit exists. Exists. It's 5. Right here. Well, the other one here, limit did not exist. That's why I like this question. You have an example of non-removable discontinuity, and you get an example of removable discontinuity. At both places, there's a problem. There's a jump here. And how do we call this? When there's a removable discontinuity, what's the word for that we use? A hole. We'll say it's a hole. Listen, you have to describe things like that. It's okay. At least still describe it like there's a hole. A hole is a removable discontinuity, but the proper way to say it that the limit exists. Okay, and one more. Number 3. One more. One more troublemaker. So we look at this one, that one, there's one more. 3. What's up with the 3? What do you see at 3? And there's no even f of 3, right? There's no f of 3. If you look at the 3, there's a no equality here and there's no equality there. So there's no point. So that technically is the same thing as at 0. Do you agree? Same problem. There's a jump. There's a bigger jump, but still a jump. And for both places, there was no point. That f of 0 does not exist. Here, f of 3 does not exist. So yeah, f of 3, well, you said it. Let's write it down. F of 3, DNE. But the limit right here, let's write it what it is. What is it from the left side? That's left. Remember, you read the y values when you say, what is the limit? What is the derivative? What refers to the value? While where is what x coordinate. So limit as x approaches 3 on the left side is -5. Okay. And what is it on the right side? So left is -5, and on the right it's +5. Yeah, +5. So this is 5, this is -5. They are not equal, therefore limit does not exist. And what do we say? Discontinuity is removable or not? No. Not removable. This is why in pre-calculus we spend so much time on piecewise function, because only they allow us to come up with these examples where things jump. Other than the jump, the greatest integer function. But if you have a function that is defined just regular way, like x squared plus 5x plus 7, the only problem that can happen is when you divide by 0. Otherwise, the only troubles that you can create is by having these pieces. So that's why we do spend a lot of time on them in pre-calculus, and we do use them extensively in calculus. All right, let's go on to the next question. So that's it. So we got 3 discontinuities, 2 of them non-removable jumps because of the limit being different from both sides, and the other one is removable hole because of the fact that limit does exist. So when you kind of study, you want to kind of focus on those cases. So that's a question you might recognize from one of the quizzes. Hopefully you look through them and you look at something like this and you kind of, some of you actually, there's something that I hear often from the students, right? You look at the example, you review everything, you look through all the solutions. It's going to make sense to you. Like, yeah, you can follow the steps and everything is looking good and perfectly, reasonable. But when you go and you take a test, it's all of a sudden it's like, oh, I can't do it myself. right? It's like, I don't know what to do because it all made sense to me when I looked at that, listened to your videos, it's all okay. I'm in class, I'm understanding this, but then I get to myself to do this and I just blank out and I just don't know how to start. That's a very common thing and it happens to, many. How to address this? The best way to address this is kind of reaching a saturation point. What do I mean by saturation point? I don't have a magic solution to kind of resolve that thing. I'm just making you aware of that. And the best remedy for that is a saturation point. So what do I mean by saturation point? Is where, you're looking at the question, yeah, it makes sense to you. But, how many questions have I done with this particular, skill? Did I do only the limits that I've seen in class, or have I done more limits? Did I look at the limits that are similar to that one without looking at the actual solution key, right? So in other words, you do a couple of those, right? You can look at, examples, I posted some of this website that has lots and lots of post notes, that has lots and lots of examples all worked out. But then take that example, write it for yourself, and then see, can you logic through this without looking at your notes? Does that make sense to you, right? So, again, this is not something that I just know the thing, and the best way to address it is to have the saturation where it's like, okay, this is familiar to me. I didn't memorize the question, but I understood what it was, and I was able to do it on, my own. Like, for example, this one. What's this? What is this about? What topic does it fall on? Continuity. What do I need to know about the continuity? Continuity is closely connected to the notion of the limit. This is a piecewise function. And each of those pieces, let's highlight those pieces. This is one piece, and this is the other piece. One is a quadratic expression, parabola, and the other one is linear expression, kx plus 3, where k is the slope, we don't know what it is, right? What do we know about parabola? Is the parabola a continuous function? Does it have any trouble? No, parabola has no trouble. What about linear function, mx plus b? Does that one have any trouble? No, so they're both perfectly fine. So then what do we know about the piecewise functions? We need to know something about them, and this is kind of like here. The problem with the piecewise function only happen where the branches separate. Where do branches separate in this one? Because there are only two branches in here. Where do they separate? At what value? At 1, right? You see the separation point, 1. You see it there, you can't miss it, it's 1. In other words, if I ask you if the function is continuous at 5, will it be continuous at 5? Why? Where does 5 belong? 5 belongs to which line or parabola? 5, number 5, x equals to 5. Line. There's no, doesn't matter what slope is, it's going to be okay. How about, let's say, somewhere at 0? Also going to be okay, because this has no problem and this one has no problem. The only problem happens is when the two pieces separate. They separate at 1. So in order for this to be continuous at every point, it's already continuous everywhere except at one point possible, because that's the only trouble. So the question is, how can we guarantee, okay, what is k so that f of x is continuous where? Where do we want to ensure the continuity? At 1. It's okay everywhere else. Because it can be like the only problem will come up if you're dividing by 0, but we don't. And these are two perfectly good functions. So how do you approach this? You want to approach limit on the left side. You want to approach limit on the right side. If you think of this logically, do not overthink. If you plug it in 1 here and you plug it in 1 there, they better be equal. That's it. And then, yeah, you have a fancy notation, limit from the left, limit from the right. But it's about you understanding that in order for this thing to work, if you plug it in 1, you need to get the same thing. Because if you plug it in, everything else is going to be fine. No trouble. Only 1 is the trouble. That's it. So don't overthink. It's a piecewise function. So let's plug it in 1. When you plug it in one in the first branch, what do you get? If you substitute 1 in the first branch, you're going to get, and then you see now we're kind of like, okay, we trying to kind of understand the concept. We said, okay, we have a left side and we have the right side, right? This is left and this is right. So if you put the left side is this. This is the right side. Right of what? Right of 1, because this is 1, this is right, and this is left. So if you substitute 1 on the left side, again, let's do it informally and then fit it in with the limits. What do you get if you plug it in 1? Plug in 1, you get 2 minus 1, you get 1. What if you substitute 1 inside here? You get 1k plus 3. And the answer will depend on what is your k. All right, we don't know what the k is, but that's the question is, what is the value of k to make them equal? So informally, these two pieces has to be equal. So what is the equation that we write? I'll do it one more time. All right, okay, yeah, I gotta stop here. All right, so yeah, you set them equal to each other, right? So you get k plus 3, and you're setting them equal to 1. That's the idea, that's the concept. How's that concept? All right, now, is this a difficult equation to solve? No, right? And that's the thing, it's not about algebra. This is more about understanding what we're trying to do, right? So then we solve for k, so we move the k over and we get k equals to -2. So now, if this is -2x plus 3, we ensure that the right piece and the left piece meet. And notice that equal sign is there, because if one of them does not have an equal sign, then it's not going to be continuous. It needs to exist. Okay, now what's the proper way to write it? You have the left side like this, and you have the right side, which is like that. That's how we write the right and the left, which is what did we say? K plus 3, and then from there you go here. All right, so that's the proper way to write it. Listen, I'm not really going to say, you didn't write the limit, you don't know what you're doing. No, that's absolutely okay. I mean, this is fine as an approach. You understand the concept is that the left branch, not branch, branch, and the right branch are equal. All right, so that's another, as you can see, it's not algebraic, correct? Neither questions were algebraic. There was no algebra prerequisite whatsoever. It's all concepts. Now we get to algebra. Well, kind of, not even too much of it, because these, right, the question right here, asking us to evaluate the limit. Evaluating limit is a very, if it's not from the picture, and if it's not a piecewise function, evaluating the limit has to do, what's the general process when you do limit? How do you approach limits? What do? You see a limit question. So what's the immediate thing that comes in your mind? Plug it in, right? So you got the ideas that if you want to limit, you got to find and plug it in. But then you see the additional concept is that it's not the same thing as plugging in. Limit has to do with this idea of approaching. I was just asked a question, an hour ago about, like, okay, I understand I'm substituting the number inside. I understand that I get something, but then what if I do algebra and then I plug it in and again and I get a different answer? How come, when I plug it in first and I did not get the answer and now I got the answer means that the answer is this? The fact that it didn't work before, right? The fact that you didn't get the answer when so like in this case, right? You substitute 4 and you get what? 0 over 0, correct? Why don't you just say that's it, D and E, right? I mean, you plug it in and you didn't get an answer. Why you need to do something else? All right, so student had kind of like unsettling things like, yeah, I can memorize it, I can go ahead and I have to do something, but they didn't like the fact that this becomes just like, oh, okay, I gotta do something. Why do I have to do something? Like, you plug it in. What's the problem? I mean, why even bother? Why can't you just say D and E? Right? Why can't you just say, by the way, don't write it, that's not the answer. It's not like, why can't you just say D and E? Like, you plug it in, right? 4, because that's a natural thing to do. It makes sense that you plug it in, right? It's a natural thing to do. You plug it in, you get an answer of 0 over 0 once you substitute. Why can't you just say it does not exist? Because, you know, you didn't get an answer. That's it. Why are you bothering me for? Huh? But why? Because that's a question I was asked, and I was, you know, very happy about that question, because, you know, like, why not just leave it like that? It's complicated, the question. It's difficult to answer, right? Like, why do you have to continue going, right? Exactly. You want to see what is approaching. So the fact that you plug it in, you're not actually evaluating the limit, because limit is not about plugging in. What is plugging in? Plugging in is this. This is plugging in. This is, you know, we'll learn this in pre-calculus at the beginning of the semester, even earlier, maybe even in algebra, you've seen this notation. That's what it means to plug it in. So if you plug it in a number and you get 0 over 0, what do you say? You say it does not exist. What does not exist? Not the limit does not exist. What do you say? F of 4 does not exist. That means there's no value at 4. No value means that at that particular location, and that locality, that point right here, there is nothing. There is nothing at that point. Limit is much more than that. Limit is not about the physical location at that one point. Limit is about investigating what happened to before and after. So technically speaking, if you were to investigate this, and that's how we started the semester, to understand what that limit is, it's not that you right away say, oh, okay, I do algebra. No, that's not how we started this. If you recall, when we talked about limits, we said the first thing that we're going to do, we're going to plug in a number that's really close to it, like 3.9999999. And then on the other side, you're going to plug it in 4.00001 to investigate. Unfortunately, that process is time consuming. It involves a lot of steps, like you got to plug it in and plug it in and plug it in, and it takes forever. All right. That's why, you know, technology or using a graph or something like that, then it will help, but it's not efficient. So then we say, okay, plugging in numbers like that is complicated because it is not convenient. And then you investigate further, and you try to find an expression that is equivalent. What does in mathematics means equivalent? Like, let's say, can you give me an equivalent expression to 2 over 4? What's equivalent expression to it? A half. Correct? So what do? You simplify, or you're trying to reduce it. So that's what you're trying to do, not because you have to, because of the way, you know, because this is not enough, or what it is because you're trying to find an alternative way to investigate what happens before and after instead of substituting. So that's where we get this, I think, is when we substitute 0 over 0, we say that the answer does not exist because we need to investigate it further, because 0, 0 actually indicates, and that's algebraically, you can do something to rewrite this expression and look deeper and see what's happening at 4. All right, but understand that this statement, that the value does not exist, is not the same as this same statement where you do that. You don't say that it does not exist. No, if you substitute and you get 0 over 0, which is the most common case that happens for investigation, you say, okay, I need to do some algebra to try to rewrite the expression. So we want another expression that's equivalent to it. And then you do this, and then then algebra. Okay, so that's one of those questions where, yeah, you got to use algebra. And what is that algebra that we employ? Conjugate. All right, so that's an example of a conjugate. That's an example of a conjugate. So you multiply this by that. All right, so that's where you say, okay, here's calculus ideas, and here's the algebra backbone. This is the first time so far where we needed to use algebra. Do you agree? Look so far with these examples, right? Before we didn't, but this is the first time the algebra is needed there, and then you do the math. Okay, so that's definitely where, you know, the skill, the algebraic skill is important. So you simplify this, and then what do we get? When you multiply conjugates, you get the square of the first term minus the square of the others. That you become difference of the squares, right? It's this times this, and then this times this, and the middle terms will cancel. So what will it become? Notice that I'm still writing the limit, because we're kind of going back, because we substitute before, we got 0 over 0, but it didn't help us, meaning that it doesn't tell us what happens before and after. So we say, okay, let me rewrite this expression. And you say, what? It's x minus 4, yes? They're going to reduce, right? So let's maybe put it on the side. What happens with these? I'm trying to find a remedy, right, for algebra. Like, how can we? I don't want to reteach the whole thing working with the square roots. So I'm trying to think of what's the easier way for you to see. Okay, so look, if you're absolutely maybe not comfortable with this, then yes, you can go ahead and FOIL it like this. You multiply it like that, and it's just a lot of writing. You see, it's like that. Whew. And then these two cancels, and you ended up with x minus 4. I don't suggest doing this every time. You know, at calculus level, this is a little bit, it's like, you know, when you see it for the first time, yeah, you will do it like that, and then you will simplify this, sure. But it's much more convenient to deal this with that when you have the conjugate. Since we see conjugates enough, right? We can generalize it. So check this out. When you have something, let's put it like this. Square root of b minus square root of a multiplied by another square root of b plus square root of a, right? That's how we dealt with these things. Then you get what? I'm trying to patch the thing, but I want to make sure that it's not. I'm thinking of the way to present this so it's easier for you to see. Maybe let's. How about this? I mean, are you familiar with this formula? A minus b times a plus b equals to a squared minus b squared. How about that? Is that okay? Difference of the squares, right? A minus b times a plus b equal to a squared minus b squared. So when you see conjugate, you have one squared minus the other squared. How about that? Do you see it? Then it's square root of x minus 2 and square root of x plus 2. That kills the square root. All right, okay. So then what happens is that, so I'm adding this additional step just so kind of, all right, so let's just put it like this, and then x minus 4 will square, you're absolutely right. So that will reduce. Well, when you reduce it, it's the numerator doesn't disappear, okay? It becomes 1. I see this often in algebra. It's like, yeah, you did this work, but the 1 is still there, right? It doesn't, the fraction doesn't go away. You still have 1, and then you plug it in, and you get 1 over square root of 4 plus 2, which is 1 over 4, right? 2 plus 2. Now notice, when we plug it in at first, it did not work. Now it does. But then how come that answer that we get right now, we say it's an answer, but when it did not work, we said that we needed to do more? That's a confusing concept, right? It's like, why did you need to do all of this? And the reason is that you are rewriting this expression not to see what happens at 4. You don't do it to see what happens. You know what happens at 4. What happens at 4? What happens at 4? There's nothing at 4. There's nothing at 4. And you might say, okay, but I'm substituting the 4 and I get something. I get a quarter. Well, that does not tell you that there's a quarter at 4. What it tells you that is you choose a number close to 4 on the left and you choose the number close to the 4 from the right, it's going to be close to 0.25, which is a quarter. And the reason why we're using this expression to investigate, because that expression, this expression, 1 over square root of x plus 2, it's the same expression as this. Because what we did is we multiplied top and bottom by the same thing. This expression and this expression, the one that we simplified right here. And since I'm doing it on the screen, I guess I can highlight this. Okay, this expression here and this expression right there, they are the same. They're mathematically equivalent, with the exception at the value of 4. But because we are trying to find the limit, if you choose a number on the right of 4 and if you choose a number on the left of 4, you're going to get something close to a quarter. And that's the answer to the limit. It's not a simple idea. Limit is not just a mechanical process. Limit is the investigation. So I would suggest that if you want to understand this better, graph this. Put a number to the left of 4 and to the right of 4 to convince yourself that the answer becomes close to 0.25. Okay? Okay, how about B? Did you get a chance to do it? It seems to be, some of you did. By the way, you can always move on at your own pace too. I'm going to go over all of these questions, but yeah. So for the first one, for the one that we just did, the answer is a quarter. The answer is a quarter. The answer is a quarter. That's the answer to the part A. The answer is 1/4 because once you substitute 4 now, we were able to get the result. That means that the limit is 4, a quarter, because we are getting an answer. So definitely when you're studying this, yeah, when you do the limit, your initial instinct of substitution is correct. And depending what you get, like you get 0 over 0, it tells, okay, I got to do algebra and then plug it in again. All right. Yes, you can remember the skill. You can get comfortable with this. And then if you're asking a deeper question as why, okay, you're on the right track. But for now, to prepare for this, absolutely, you plug it in. You get something. There are not that many things you could do. There's a factoring and there's this. That's it. I'm not going to ask anything else. I mean, we'll also have the trigonometric limit, sine over x, you know, those two special limits. But other than that, not that many things you could do. I'm going to erase this, okay? So it's not really needed. All right, so what happens with the other one once you substitute 1? What do you get? You get 1 over. Or you even try to simplify it, right? Yeah, that's very nice. Yeah, so you figure out that there's something that they have in common. You try to simplify this, and that's interesting. 1 over 0. All right. So once again, if you substitute that inside the function, what does that mean when you substitute and you get, you know, you get something like this? You get also 1 over 0. What does that tell you? Excellent, Irina. Yes. If you substitute 0, I mean, you substitute something and get number divided by 0, this does not exist. Doesn't exist. Just like that. There's no value. It's the same thing. But the answers to these questions are totally different. That's why I wanted to put them together for you to kind of compare. All right. I tried to put everything kind of on the same sheet, just all the concepts together so you can kind of see them. Yeah, you got the same idea. There's no value. But this one has 0 over 0, while this one has number divided by 0. And then some of you already making connection. Yes, it's a vertical asymptote and all of that. Yes. How do you know what happens? Yeah, it does not exist. But algebraically, what that means is that doesn't matter how hard you try simplifying, that number right here, that's not going to go away. It's not going to become zero all of a sudden. There's going to still be a number, something other than zero, and the zero will be on the bottom. In other words, there's no way we can change it so it would exist. And dividing a number by zero, telling you, well, since you investigate the limit, doesn't matter how much you try, it will not change it to something that's going to look different. Zero is zero. Mathematically, it means you can change it to something that will make it work. While number divided by zero, you can. So then you start investigating by substituting numbers on the left and substituting numbers on the right. All right, so what happens when you substitute x equals to 1 from the left side? How do you approach this? Well, first, since you get 1 over 0, it doesn't exist, but 1 over 0 tells you that you have some kind of infinity. Yes? And then you've got to investigate it, which kind. But it's you already know a lot of things. You know that you don't have to do algebra. You can already write that it's a vertical asymptote and say limit does not exist. It's infinite, and just be done with that. What did the question say? If the limit does not exist, explain why. Well, the limit does not exist because from one side and from the other side, it's approaching some kind of infinity. So what is it? On the left side, you have to plug it in. So there's no easy way to just to see it. But once you approach it from the left, choose a number that's close to 1. It doesn't need to be too far away. 0.9 would work. So that would be 0.9 over 0.9 squared minus 0.9. Is that what we're getting? That's positive over negative, so that's less than 0. Oh. So that means that this is going to approach negative infinity. And then the other side, if you approach 1 from the right side, you choose something positive. I mean, something on the right side. So that would be 1.1 divided by 1.1 squared minus 1.1. And that would be something that would also positive. I mean, here's positive infinity. So you get a vertical asymptote at x equals to 1. Removable or non-removable discontinuity? How about the one in part A? Is this one removable if it was if the question dealt with the function at 4? Is it removable or not? Limit existed here. So will that be a removable or non-removable? That would be removable. You will find similar questions again. We've seen them before. I'm just emphasizing, the types, right? So we got the limit exists, removable discontinuity, involve the conjugate. You got an example where you divide number divided by 0. You got the vertical asymptote. This is a little harder case because you got to investigate. Because this one a little unsettling, right? You have to approach it from the left. You got to approach it from the right, and then you plug it in small numbers. It's kind of like not precise. With the algebra, at least you get some satisfaction of reduction. Here it's kind of like on the one side is negative and the other one is positive. So here it goes. All right, with question number 4. We had a quiz on that. Then we have a makeup quiz that was on Blackboard. I'm going to try it for the 3rd time. All right, I'm going to try it for the 3rd time, which is with this function. There's no algebra problem, but I'm going to try it again. Something very similar. All right, where you have a fraction, a rational function. It is factorable nicely. Can promise you it's factorable nicely. It's something that's going to get reduced. And the question is, determine what kind of discontinuities are there. There will be two. One of them is removable, and the other one is not, right? Now, check this out for yourself if you haven't done it yet. You've seen through some of the quizzes, you've seen through the reviews. Here's now, the question is similar to what you've seen, right? So that's a question about the saturation point. When you see something like that, do you know what needed to be done? Do you recognize this question in terms of continuity, right? When we see the limit question, our instinct was to plug it in. When you see a question like this, what is your general instinct here? You know, you see a question like that, what's your general thing that you really want to do? And it shouldn't even happen in calculus. It would have happened if you were taking introductory algebra. Well, not introductory, intermediate algebra. If you've seen this expression, the natural thing to do is to do what? Factor. And the fact that you have x minus 1, the denominator better maybe have a 2. It doesn't need to, right? Doesn't need to. Does it happen here? I don't know. It doesn't have to, by the way. It doesn't have to. But it shouldn't be difficult to factor this. Yeah, so what are the factors? Plus. And then you can get so excited that you forget what the question was, right? That can happen, right? You see this is like, yeah, I've done it. What do I need to do, right? Like that could happen because, you know, you see something like this and it's really tempting to like, okay, here. Oh, yeah, but there was a question, right? And the question was what? It says, find the values of x for which f is not continuous. All right, so before you jumping and getting excited about factoring that you factored, and it feels good, I know. Like it does feel good when you recognize, you know, something and then it factors and fine. But then the question is, what was I asked to do? Where it's not continuous. So if you look at that expression before you reduce it, can I like go back? Here we go. Before you get reduced, this is what it is, right? And you see there's a fraction. And what do we know about the fractions? What do we know about functions and fractions if you talk about continuity? What's the first thing that we have to consider? The question that in my pre-calculus classes I bothered on every single day. Domain. Absolutely. We have problem over here. We have a fraction. Right? In our pre-calc classes, I used to say, you know, every class we introduce something. What is the domain? What is the domain? Why did I say that? Because the domain is a gateway to continuity. Because if something is not in a domain, it's not continuous automatically. So what's the domain of this friend? X cannot be equal to -2. And x cannot be equal to. Is that okay? Right? Yes, you with me? These two numbers are going to make the denominator 0, and dividing by a 0 is not 0. I'm hopefully not going to see that, hopefully on Wednesday, right? Is that, you know, you got a 0 in denominator and say answer is 0. You do a limit question, right? The worst thing that could happen, I start crying. That's why, you know, when I return the test, you see a little like, you know, on the paper with this water, like it blows up. You'll see that right at that place where you wrote this. Like if you see that 1 divided by 0 and you say it's 0, that's it. I'm just like start hysterically crying. My kids are writing, you okay? Is everything fine? Dividing by 0 is one of the most fundamental concepts in, you know, pre-calc and calculus analysis, just in general. Dividing by 0, not only that the answer does not exist, but there are two things can happen. You either have a removable discontinuity or you have an asymptote. All right. And that's where you're kind of going to see that. You want to understand it, not just to memorize that too, right? But definitely not to write that something divided by 0 is 0. Okay. That's like in calculus, that's definitely the, like, you know, there are sometimes they say, you know, some mistakes are okay in calculus. And let me say that straight. That's not okay to do. And then it's not, you know, it's not me not being nice. It's just, I do really want that to stay in your mind is that dividing by 0 doesn't exist, and then you investigate, right? So you definitely don't want to say that the answer is zero. Okay, fine. So without more yapping of that, let's finish it off. So we got two problems. So that's where it's not continuous. Why it's not continuous there? So not continuous at x equals to -2. Why it's not continuous there? But why it's not continuous there first? Why do you say that x equals to -2? It's not continuous because it's half of the. We answered half of the question that it's not continuous at these points. Why it's not continuous there? Because it makes the denominator 0. All right, that's why it's not continuous, because it makes the denominator 0. Or if we write it fancy, we say f of -2 is, what is it? Yeah, but just in, like, when you write this notation, f of -2 is, does not exist, right? So not is, but does not exist. Correct? That's what we say. We say that f of -2 does not exist. That's why it's discontinuous, because that's what the question asks first. Find the value, the x values at which f is not continuous. F of x is not continuous at -2, because f of -2 does not exist. Done. That's part of the question is done. And then the second one, x equals to 1. Also, it's not continuous. Why? Because f of, for the same reason. Oh, jumping. Okay, here we go. F of 1 does not exist. Good? Yes? You with me? So f of 1 does not exist. So this does not exist. This does not exist. Both of them do not exist because it's not continuous. But then it says which of the discontinuities are removable, meaning that, you know, there's a classification of non-removable or removable. So that's a third question on this handout. They're talking about this removable or non-removable business. How do we know that something is removable or not? We compute limits, because limit is an extension of this idea, something that we were missing in pre-calculus. All right, so now you talk about removable, so you do the limits. And that concept is not easy, right? It's not, you know, again, easy or hard, it's very relative terms. But when you say limit, the first thing comes in mind is to plug it in, but we already plugged it in and we know that it does not exist already. But when you substitute value inside the expression and you get something that is not defined, when you do the limit, it does not tell you what the actual limit is. The limit is a more bigger concept. So for instance, now you see, if you substitute -2 inside here, right, that would be the same thing as if you were to reduce this. Now you get excited and you cancel. Not all the way even from the beginning. And then, listen, of course, there are like a visual clues that can help you, like, again, just to help you out as we're reviewing for the test. What happened right now? We reduced. So you kind of remove the discontinuity. I mean, that's one way you can think. That's not a proper way to think about it in a way, but it's, you know, you can justify that statement. You remove the discontinuity, or it is a removable discontinuity because that factor can be canceled. And therefore, once you're finding the limit now, you see if you plug it at -2 is still going to be there. Because if you plug it at -2, what do you get? You get 1 over and 1 over 0. First of all, it's not 0 still. Okay, that's still not 0. It's still, you know, it still would be not a good thing to say that it's 0 because it's not. But now 1 over 0 tells you that not only the function does not exist. We knew it from before. But now the limit is 1 over 0. It tells you that you encountered an asymptote. You know that there's a vertical asymptote at x equals to -2. Why? Because this concept of infinity, the infinite limit, approaching from the left, approaching from the right. So yeah. Well, when you substitute 1, what happens when you substitute 1? Inside here, because it's the same expression, what do you get now? 1 over, but that exists. So that tells you that not that the value is 1 over 3, it tells you that you have what kind of discontinuity? Removable. So if you kind of like crash studying for the test and you're trying to see, so how can I get this question to work out? Factor it out, determine what are the discontinuities. There are 2 of them, okay? One of them will have a limit, the other one doesn't. The one that has a limit, we say removable discontinuity, that's the factor that got reduced, while the other one gave you the vertical asymptote. All right. Conceptually, it's you know, it's not straightforward thing, but now as we're reviewing this, you want to find a way for you to kind of structure this. Okay, let's go on. The shorter questions here, relatively speaking. Classic question on finding the equation of a tangent line, right? So at a point. Now notice I'm giving you both x and y. X is given and the y is given. That is the point on the curve. How can we double check? I just made it like an hour ago, this review sheet. I did make some adjustments of using my questions from previous exams. I just want to make sure that I didn't make a mistake here. This is x, this is y, right? So if you plug it in, x equals to 1 inside the expression, then would you get -2? If not, then I was rushed through it. Is that okay? F of 1 is -2? Okay, good. Okay. And why am I saying this? If the y was not given, you would need to do that to find the y. Because you need both x and y to write the equation. And then your answer will take this form. Or the other one, y minus y1, it depends. It looks very few of you use this form. In calculus, it is more efficient, but not many of you like it. But either way, especially when you're given the point, this is just easier to use in a way. But again, I don't want to force you to use either way. But notice that for either one of them, we need the slope and we need the point. Point is already there, the slope, which is what we study calculus for, right? Calculus is the study of slope. So how do we get the slope out of this? What do we need to do? Interderivative, right? So we need the derivative function. So the slope is the derivative. Okay, so derivative here is not bad, all right? Or hopefully does not look bad, right? It's a regular power rule. So what is it? 4x minus x squared. And then we need it at a point, so we need to do what? Plug it in. What are we substituting? One, x, right? 1. This is your x, this is your y. All right, so once you substitute 1, what do we get? -8, right? That is your slope. Let me just erase this like this, so it's not multiplication. Let me just label it. This is the slope at that point. Notice we didn't need to know y to find the slope because the slope is only dependent on x because it's a function. If it was an implicit equation, then we needed both x and y. But since it's a function, we just need an x. How's that? So look, the slope is not this. This is not a slope. 4x minus 12x squared, that's not a slope. It's an expression that gives you the slope at any point of x, but you need the slope is a number. Slope is not a function. Because I know the very common mistake, it's not a bad mistake. There are bad mistakes. Dividing by 0, that's a bad mistake. Taking this whole thing and substituting that in here, it's not as bad of a mistake, but you got to realize is that this is not a slope at a point. It's a slope expression at the point that you need. So for example, now what we need is the point that's the slope. That's your M. That's your M, not that. Once you plug it in, it becomes an M. Okay, and then algebra. Okay, so here there's nothing I could do about it. Honestly, there's nothing I can do about this in calculus. Is the way you find the P, right? So that question is at any level of math, doesn't matter what level of math, somewhere that pops up, this particular thing. All right, so I'm gonna just do it quickly. So move 8 on the other side, it's 6, right? So it's minus, so the equation becomes minus 8x plus 6. And we can double check. If we substitute 1, it will give us -2, so that's good. And then you got to ask yourself, again, after we have the midterm, I told you that we would need to have some kind of, conversation or something like that, where we have to see how we're going to continue with the class. Because, I mean, the stuff like that right here, all right, that's definitely something that should look very, very much familiar. All right, let's go on to the next question. The most important part is finding derivative, substituting, and getting the M. All right, let's go to the next one. So question number 6 is application of what rule? It's asking us to differentiate this. Chain. All right, let me give you maybe a few seconds if you haven't had a chance to compute it, I didn't put any sines or cosines in here. Just, kind of seeing what it equals to. How's it going? I'm gonna write it down. So we're using, so this is, what is it called? This is the chain rule. So the derivative. So notice how the inside stays the same. Here we go. All right. And then you keep the inside. Yep. All right. Thank you. So how does that look? Right. Now notice that. Thank you so much. So when you look at this, is that when you applying the chain rule, the inside stays the same. Right? This thing that doesn't move, and then you take a derivative of this later. Is that okay? Yes. All right. So you don't want to do two things at the same time. All right, so the most common mistake would be to kind of like do 6 and then 14x and then square all at the same time. All right, so that is the calculus. That's pure calculus rule. There's nothing from algebra that is kind of like needed, right? It's something that visually to see, you do need to see a composition. That's one is inside the other. Okay, let's go to the more recent topics. You know, we're getting to the end of this. So let's go. Oh, jumping. Okay. Yeah. There are two questions in here. So for number 7, there are two questions. One of them is asking to find dy dx, which is the derivative. And then the second question is to find the second derivative. There are two questions in one here. So let's go, and then it will give us, you know, a little practice dealing with the implicit differentiation. Okay, did you get a chance to? I see some of you got a chance to do it. Yeah, let me give you some time to see if you can definitely focus on the first derivative. See how you can differentiate this, especially differentiating this XY combination, right? The product of X and Y. Yeah.
How would I finish this? I don't know if I did this part right.
This is the second derivative.
Yeah. I don't know if I did it. I tried.
Well, we have to make sure that this one is right.
Oh no.
Here's your cosine is negative sign, so that will
There's
change
already a
it.
minus, so-
Okay, then you moved everything away, and this is what you got. Okay, so this is good. And then you have to use the, for this one, you have to use quotient rule.
Yeah, and I tried over here. This is the second. This is the first.
Okay,
This is the
okay, so you got the square of the denominator. And then you need to differentiate this, which is minus dy dx. And then minus cosine of x. Where's your minus cosine of x? It's right here. So you leave it like that in parentheses. And then,
confused.
yeah, because you see you have a bottom and you have the top.
So I did the quotient, and this is what I got. I did minus dy dx times the x.
Yeah, but you see you did dy dx, that this is together. This is not multiplication. This is one numerator. So you want to cheat it together. Got it?
Wait, no, but isn't it minus dy dx minus cosine?
That would be one part. That's in parentheses. That would be the derivative of the numerator.
Oh, I see what I did wrong.
Okay, but yeah, you're on the right track. Okay, good.
Minus u v prime.
Mm-hmm.
Okay.
Yeah. And then you identify what is your u of v or what is your f and the g. Okay, let's write it nicely. All right, so we got the x, we got the y. We're not doing anything. I'm just writing it big. I just realized when I wrote this question, if you look at this function, I mean, if you look at that equation, if you think about this, just, you know, if you look at this, you know, I just noticed it myself, you can actually get y by itself. And if you get y by itself, then differentiation becomes normal. But that's not the point of implicit differentiation. The point of implicit differentiation is to deal with the expressions where you cannot get y by itself. But since it says by implicit differentiation, it's still a question that we can leave this way and review the implicit differentiation. So let's pretend we didn't notice. So we'll just go ahead and differentiate this. How do we differentiate this implicitly? We use you're using u and v. So I'm hearing u's and v's. So if you want to use u's and v's, let me use u's and v's. In class, we use f and g. So it depends. Again, it depends on you being searching for ways to understand this rule, which is great. So if you use u and v, then what is that? How does that work? U prime v. Okay, so that's that way. Now, if you were studying with f and g, it's the same idea. F prime g plus same thing, is just labeling them slightly different. The point is that you do not want to take derivative at the same time. So it's not prime times prime. It's not differentiating at the same time. Okay, so whether you call them u or whether you call it v, we're gonna write it like this. So it's going to be the derivative of x times y plus you keep the x, then you differentiate the y. So I'm writing it this way just to kind of see what is what. So what's the derivative of x? That's 1. So this right here is I. Okay, that's 1. And what's the derivative of y? So some of you writing this as y prime, some of you writing as dy dx, some of you can write it as 1 times dy dx, but that's the idea of the implicit differentiation. Okay, how about the cosine? Derivative of cosine, since it's just a cosine, there's no rules needed to be done. Just remembering what the derivative of cosine is. So what's the derivative of cosine? Negative sign. So that means the negative and negative will change into positive. So that would be minus minus. Just so we can see where things are coming from, right? And then equals to the derivative of 2. What's the derivative of 2? 0. So here we go, we differentiated this. So then you can write what dy dx is. So you're trying to isolate it. So we can have this one right here. And then got the y. Okay, let's take an extra step. And the goal is to isolate this by itself. So we got x dy dx equals to. So if you move y and the sign on the other side, both of it will get negative sign, right? It's negative y, negative sign. And then we can divide both sides by x. So minus y minus sine of x, and the whole thing divided by what is it? Dy dx. Oh, what? Oh, I don't know why I wrote it like this. Okay, what do we do next? So that we answered the first part. So do the second derivative using implicit differentiation again. So that means you have to differentiate it one more time. All right. And to differentiate this one more time, we need to use a quotient rule. All right, I'm just seeing where we can have space. I guess is this. Let's try to squeeze it in. So d2y dx squared. So that's the second derivative. Does it move? No. Okay. Differentiating a quotient. Again, whether you use the ratio u to v or something else, what do? We have the denominator gets squared, and then it is what's in the numerator? U prime v. All right, so immediately we square the denominator, so the denominator becomes what? Now we need to differentiate the numerator, keeping denominator here. So we need to take the derivative of this, correct? And to differentiate this, there's a little bit of work involved. So what's the derivative of? I'm just want to see because I usually use OneNote, and this is on my on Word. Okay, fine. So yeah, what's the derivative of negative y? So we're differentiating this. So what's the derivative of negative y? Negative dy dx, so y prime. We're gonna have not enough space over here. And what's the derivative of negative sign? So it's minus cosine because derivative of sine is the cosine. I'm running out of space. Let me try to make this. I'll copy over here because it's I don't need all the space here, so I'll just move it. We don't have to simplify this, but just to sketch out the steps, right? So d2y dx squared. Yeah, so we keep the denominator squared. All right, so we take the derivative of this. So it's minus dy dx, then minus cosine of x. That's it. We differentiated this. This is going to be our u prime. Now we need to multiply it by v. So we times it by just x, correct? Then we got to do minus. Now we're going to keep this mess here. And now we got to multiply it by the derivative of x. What's the derivative of x? 1. That's it. Well, for now, let's just make sure that we see where things came from. Because this one is a little, it's a lot of pieces going on. We got the denominator squared. This stuff in the first parentheses, and you want to enclose this in parentheses. That's the derivative of that. You keep the bottom. Minus, then you keep the numerator, because we already differentiated it here. And then you times the derivative of x, which is 1. So that's the application of the quotient rule. Now, to just make that look scarier, technically, right? And, not necessarily you'll see something long like that on Wednesday, but, the process itself is here, is that dy dx will get replaced with this. We plug it in. And then you can clear all of the minuses and pluses to make it look more compact, right? I'll write it, but again, that's, it just becomes a little bit scarier because algebra can get messy when you're dealing with the second derivative. So it's minus dy dx. So this, all of that stuff right here, you see that? That will be replaced with all of that. So you got the minus, and then it gets replaced. So it's like this. And then the rest will stay. Yeah, it's not the, and there'll be some reduction. It's gonna look nicer, but that dy dx, all of that will get replaced with this. Oh yeah, no cosine. Yeah, and also the cosine. Absolutely, absolutely. You're paying attention. That's good. Yep. So minus sine minus cosine x, and then you do have that minus cosine. So let's see that we plug it in nicely over here. So hold on. So it's minus dy dx. So that's minus dy. And then you got minus cosine. Yeah, not a great question. See, that's when you try to come up with more examples. And that one question end up being annoying. Yes?
What is the minus cosine of b?
All of that is going to be in parentheses. It's going to go in parentheses right now. So all of that will go in the parentheses. And then you have the rest. And that minus sign can be distributed. Yeah, not a great question. Sorry about that. Yeah, this one ended up being a little bit over the head. And technically you can distribute this and get rid of the fraction, but I don't want you to study something that's not as crucial. Okay, I don't want to confuse you. So I wouldn't focus on that second derivative here. The first derivative is fine. That's fair game. The second is not. It's a little bit too much algebraically. Mm-hmm.
The last sign one.
This one, it turns into a plus because of that minus distributed. It's x. It's just it's an x. There's no y there. It's an x. Let me get you back to more important stuff. All right. So again, it was my oversight. Again, I tried to prepare additional questions. It was already a lot I did not have that. I added on the second derivative. I had the first derivative asked, and the second one I decided to add on. Again, let me make it clear, and if you also, anybody who's watching the recording, is that that's not something to focus on, but I need to get you back. I know you're tired, but we still have time, and I want to use time efficiently. These last questions, these were copied from last semester's exam. So that means that I have to, I edited this a little bit. They're not long questions. 8? Oh, yes. 8, and then this is also, I want to make sure that we have enough time to go over this. For the past couple of weeks, I've been bothering you about this idea of continuous versus differentiable. The best way to understand this is by looking at pictures. Look at this graph that you see in number 8. What is the domain of this graph? Let's do some pre-calculus. What's the domain of this graph? -5 to? Oh, hey, flip back. What's -5 to? 6. 6. Why are you saying 5? Oh, that looks like a 5? It's, I mean, we can count. 1, 2, 3, 4, 5, 6. Remember, domain is the x. Are we okay? Yes, yes, yes. Okay, okay, okay. -5 to 6. What about the range?
0 to 5. Wait, no, -1 to 5.
-1 to 5. Okay, fine. Why am I asking this? Well, we need to go back to the idea of continuity first. Where the graph is continuous, on what interval? On its whole domain, right? So domain is not all real numbers. Domain is starting at -5 and it ends at 6, correct? So that is the interval of continuity. It's the same thing as the domain. That's it. So where's it continuous? Continuous. I'm gonna write it like this: continuous on, not from, but on. Continuous on, just like you say domain. You say continuous on, and then you write the domain. Let me ask you this question. Idea of continuity. Do you see it just visually that it's continuous? We don't take a pen away from the paper, right? There are no breaks, correct? You see it's continuous everywhere. It's all fine. There are no breaks. We don't know what the equation for this function is, but there are no breaks in it, all right? So it's continuous on that interval. Idea of differentiability is much deeper than that. Idea of being differentiable, and that's why I use that word in bold. Differential means having a derivative. But what does it mean having a derivative? Having a slope. And slope is a local event. Where does it have a slope? And that's why you had that last quiz and review the, the answers. I posted the key again on Blackboard. Definitely, review those questions there. But if you look at the graph, you ask yourself, for example, can I find the slope here on that interval? Can I find the slope? What is the slope there? You have it also printed, so it's easier to see. What is the slope? Go up and over. So you go up 0 to 2, so it's 2 over 2. So that slope is 1. Yes. Hey. Okay. I'm writing this using, algebra notation. Slope is 1. How about the next piece? This one. What is the slope there? It's hard to count, but you said it goes down 2, 3. So -3 over 1, 2, 3. -1. Okay. Does that sound familiar? Like you've done this before? Rise over run? That's exactly what the calculus is about, but not just rise over run. We have more different things that can happen. But derivative as a slope, sure, at a point. How about the next piece? I'm playing with the colors right here. I figure it out, so I'm excited. All right, so here's another color. All right. Oh, what does that do? Okay, so what's the slope here? Whoa. 2? I trust you. All right, and what about the last piece? 0. Hooray! All right, slope is 0. Okay, so here you got those slopes. So you got the slope equals to 1, -1, 2, 0. Guess what? Those are derivatives. Those are derivatives. So their derivative every, we have the derivative. And now the key point, which I tried to emphasize on the lab, we tried to see it on Edpuzzles, we tried to see it in class. What happens when the slope abruptly changes from one number to another? In other words, let's say you travel here on a yellow road, right? You're traveling and it's okay, it's going fine. You're climbing. You reach the peak and you look up and then there's this sharp thing right here. There's an abrupt change from 1 to -1. Exactly, we call it a corner. We encounter the corner. The question is, we know that if you look on one side, the slope is 1. You look at the other side, the slope is -1. You're standing right at that corner. First of all, do you have a place to stand? Like, is there something there to hold you? Yeah, you have a point, which is, what is it? 1, 2, 3. That's -3, right? So so let's make it super, super clear. What is f of -3? Oh, it's even labeled. Okay, great. Is it continuous there? Yes, because you got a point. But now question about differentiability. Is it differentiable there? If you're stating at that thing, is there a slope? Your first intuition might be, oh yeah, well, it's 0 because I'm kind of like, but the corner is not a smooth transition. If you think of something that is like in real life that has like a corner, like a peak, you can't balance it that well. Maybe you can. I don't know, you might be able to balance, but it's not like you have a plateau where you can stand, right? Mathematically, what happens is that the slope abruptly changes from here to here. So to make a long story short, derivatives do not exist at the corners. There are no derivatives there. The derivative there is D and E. There's no derivative here. There's no derivative here. There's no derivative even here. Why? Because there's an abrupt change from one number to another. So if we were to graph this, and we're going to talk about graphing derivatives in the next chapter, all the next chapter is about graphing. Graphing. We're going to be graphing a lot of functions. The derivative at those points does not exist. 10? Oh yeah, getting there. Right. So let me just write down what we got. So the different where it's not differentiable, we say that f of x is not differentiable. Not differentiable. And let's just write them down. So what is it? At x equals to -3, 0, and 3. Now, what about -5 and 6? We do not include them either, because those are the places where graphs start, so we don't really know what happens before and after. So you don't say that it's differentiable at those points either. So it's also not differentiable at -5, and it's not differentiable at 6 because of the fact that you don't know what happens right after. So that's why when you say differentiable, you're including an open interval. So you'll include them as well, the endpoints. All right, let's go through this one quickly as the time we're almost done, but I don't want to write down the solution right here. So this is the function. That's the way it's defined. And you have to compute the derivative of this. This was similar in the way you had in the other quiz, and review the key, the last one, number 5. But this one is more where you're getting, the information is provided just in the list, but it is symbolic, meaning when you see this right here, do you know what rule is this? How do you differentiate this function, f of g of x? It's a composition. What rule do you use? Chain rule. So you do the derivative of the outside times the derivative of the inside, and then you got to plug it in. What are we plugging in? 5. So that becomes f prime of g of 5 multiplied by g prime of 5. All right, let's continue going. So we go from the inside. What is g of 5? G of 5 is 4. And now you read it and you see what is f prime of 4? Do I have it? 8. And what's g prime of 5? 3. So 8 times 3 is 24. So that's one. What about this one? What rule do we use here to differentiate? Another chain rule. So then z prime of x is going to be, you put 4 on the outside, then you have f of x, and then to the power of 3. So you use the power rule, and the chain rule is the one that will dominate that. And now if you want z prime of 4, it becomes a big number. Yeah, I mean, I was just making that up using the question from my other exams, but I did change some numbers. So I got something really big. Oh, because it's asking to find z prime of 4. All right, so we're plugging in 4 everywhere. All right, what is f of 4? Oh yeah, big number, 7 cubed. And what is f prime of 4? All right, so I'll leave your answer to your imagination. Or to your calculators, okay? All right, doesn't matter what it equals to, not important. What's important is the process, right? Is that you understand how the chain rule is working. So check this out. So number 10, it's the last question that I'll ask, the last thing that you need to review after the implicit differentiation. So this we did not do in person. That was a puzzle that I think I shifted a little bit more to encourage you to watch it. It wasn't about implicit differentiation. It has to do with the inverse function. The idea is this, and I'll abbreviate it, make it brief. First, you start off with evaluating, I scaffolded it the same way. So let's evaluate f of -1. What is that? Three minus 2 times -1, that is 5. You're right, absolutely. 5. And then you ask to compute the derivative of the inverse of 5. And there's a theorem that says that when you're differentiating an inverse, let me write it like this. The derivative of the inverse function, like you differentiating the inverse, would be 1 over, so instead of being the derivative of the inverse is going to be reciprocal. So it's going to be 1 over the derivative of the original function evaluated at the value of the inverse. Oh, look at this. Just in time, it's going to die. All right. Yeah, this is it. If this looks not familiar to you, because this was on something that is on the last ed puzzles, if you like to watch it, it's there. It's an inverse function, but the idea is that the derivative of the inverse function in pre-calculus, the inverse is where x and y switches. If you remember anything about x and y switching, and I do a little review. The part 1 in ed puzzle is the review of pre-calculus, and part 2 is the calculus. Right, so I talk about what the inverse is and how you find the inverses and the graphical meaning. It's a lot to say, but with the calculus, there's not a lot to say. Is that the derivative in the original function the derivatives are reciprocals. They are 1 over. So what do you do? Talking about what do? You find the derivative of this function. Like, what's the derivative? Negative 6x squared, okay? So the derivative of inverse is going to be this thing here, but reciprocal, meaning it's going to be 1 over it. Hey. It's going to be reciprocal. So you don't change the sign. It's 1 over it. But what you plug it in here. You're not going to be substituting 5 in it. You're not going to be substituting 5. You're going to be substituting the number that corresponds to 5. So since 5 is the value of the inverse, that means what you're going to be substituting, substituting the x. You're going to be substituting the x, which is that one right here. So instead of substituting the 5, you're going to be substituting -1. In the inverse. I mean in the derivative. So instead of substituting this, you're going to be substituting that. I'm sorry, but I can't in 5 minutes explain to why right now. Yeah, you're going to have an inverse function. So if you want to see this, it's the last puzzle that is there. The very last one, I made it available. I mean, it's always available, but this is explained in the last puzzle as to why. The process itself is not long. You got to find the derivative. You do 1 over it, but instead of substituting the number that's there, you substitute the one that corresponds to it, which is the value of the inverse. All right, so writing this using a notation, you see this notation right here? You see this? This notation? You know what that means? That means the value of the inverse. So if f of -1 equals to 5, that means f inverse of 5 would be equal to -1. So writing it a little bit neater, let me write it a little bit neater so you can understand sort of the notation. The value of the derivative, derivative of the inverse equals to 1 over the derivative of the original function, evaluated at the point of the inverse. So what that means is it's going to be 1 over f prime, but instead of substituting 5, you're going to be substituting the x that corresponds to that 5, which is f inverse of 5. What does that mean, f inverse of 5? Well, look, guys, if f of -1 equals to 5, then f inverse of 5 equals to -1. If this is not familiar to you, then it's the inverse as a topic in pre-calculus is the hardest one of all the topics in pre-calculus, in my opinion. So that's why I just can't do it in 30 seconds. That's one. But I did break it down on that video as as necessary as possible, not trying to overcomplicate this, because the actual thing that you do, you take a derivative, you do 1 over, and instead of substituting this point, you substitute the other one. All right, so as a process, it's not too bad. It just takes a while to, to get there. So let me plug it in. So what is it, by the way? So it's -6, right? -6 times -1 squared. So it's 1 over -6. 1 over -6 is the answer. All righty, so hopefully this was helpful. I tried to stay extra 2 hours for you, just to try to help you out with some additional questions. I'll make this again available, this video that Zoom will send me the link. The answer key for the quizzes is still there. My recommendation is to start reviewing those quizzes first, prepare your little note sheet for the exam, and yeah, you can bring 1 note sheet with yourself. Yeah, 1.
Front and back or just front?
Front and back, yeah, but not sheet, the index card. Well, I call it an index card. Take a regular sheet of paper, cut it in half, and then you can use back and front of that half. All right, and you can do whatever you want. You can write whatever you like.
Are you taking attendance?
No.
I also can't do it like this way.
Yeah, you can also do it that way. Yeah, that's that's a good way to. All righty, so good luck reviewing, and I'll see you all on Wednesday.
The syllabus says midterm 1 and 2.
There will be second one 2 weeks before the final. Yeah, so that would be like beginning of May. I do that 2 weeks before and then the final.
So that just would be like what we learned.